Most of us use an elevator pretty much every single day without even thinking about it. We step inside, we push a button, and we just trust that this metal box is going to get us where we need to go safely. But behind those doors, there is an absolutely incredible, complex system of safety features all working together perfectly. Today, we're going to pull back that curtain and look at the amazing engineering that makes that trust even possible.
And that's a real question, isn't it? We put our complete faith in this piece of technology. So, in this explainer, we are going to dig into that why. We're going to look at the hidden dangers that engineers have had to solve for and the just brilliant solutions they've designed to protect us on every single ride.
So here's our game plan. We're going to start with what makes a good stop and get into the art of what's called docking. That's the perfect alignment. Then, we'll get into the weeds on a dangerous but totally necessary procedure called a bypass, used for maintenance. And finally, we'll unravel the elevator's electrical lifeline, the safety circuit. And you'll see how it all points to one core idea, a system where safety is absolutely uncompromising.
Okay, to kick things off, we kind of have to adjust our thinking. According to the technical experts over at Novin Pooya Lift, just getting an elevator to stop at a floor, that's the easy part. The real goal, the real challenge, is creating a perfect marriage between performance and absolute, unquestionable safety.
And that right there is the key. It's not just a bunch of parts. Every single component, from the little sensors on the door to the thickness of the wires to the control panel, it's all designed as one big unified system. Everything talks to everything else, there are backups for the backups, and it all serves one primary purpose: to make sure your journey is completely safe and seamless.
All right, let's tackle our first engineering puzzle. What happens if the elevator doesn't stop perfectly level with the floor? I mean, even a tiny little lip can be a huge tripping hazard. Well, the solution to this is a process that's way more advanced than a simple stop. It's called docking.
Docking is that final, supercritical phase of your ride. So as the cabin gets close to your floor, these little magnetic or optical sensors are reading markers inside the shaft to figure out its exact position. All that info then zips back to the motor control, which slows the elevator down to a crawl and just brings it to a halt with millimeter-perfect accuracy. It's pretty amazing.
Now, what's so interesting here is the difference between just stopping and docking. A normal stop gets you to the right floor, sure, but as you can see, precise docking, well, that's all about safety. It completely eliminates that little step that could cause someone to fall. This makes the elevator truly safe and accessible for everybody: kids, the elderly, or someone using a wheelchair. It's a game changer.
And get this isn't just a nice-to-have feature, it is mandated by incredibly strict international safety standards. The absolute maximum difference allowed between the elevator floor and the building floor is just 10 millimeters. To put that in perspective, that is less than the thickness of most smartphones. It just shows you the level of precision we are dealing with here. Okay, on to our next challenge. And this one's a bit of a head-scratcher. An elevator is designed to stop the second a door is open, right? So how in the world does a technician safely do maintenance or rescue when they need the doors open and they need the cabin to move? Well, this requires a very, very carefully controlled override.
And the source material we looked at does not pull any punches. Performing a safety bypass is described, and I'm quoting here, as a very sensitive and dangerous action. This is not something you do lightly. It's a high-stakes procedure that temporarily disables a really key layer of protection.
So a bypass is for trained professionals only. It lets a technician move the cabin, say, with the doors open, to do an inspection or a repair. But because it is so risky, the process for doing it is incredibly rigid and standardized. So how do they manage that risk? Well, it's a super strict three-step dance. First, the technician has to physically engage an inspection switch, which is often on top of the elevator car itself. That single action tells the system, hey, slow everything down to a crawl. And most importantly, even when it's in bypass mode, the absolute most critical, no way this can fail safety features, like the switches that prevent the elevator from hitting the top or bottom of the shaft, they stay active. It's a safety net inside of a safety net.
Now let's get to the elevator's electrical heart, its nervous system. I want you to imagine a single long electrical wire that runs in a big loop, and it passes through every single safety device on that elevator. Every door lock, every speed sensor, every emergency stop button. This is what's known as the safety circuit.
And the concept behind it is, well, it's just beautiful in its simplicity. It's what's called a series circuit. If every single switch is closed, meaning every door is locked, every sensor is happy,
then the electrical current flows just fine, and the elevator can move. But the moment even one of those switches opens, like a door gets nudged ajar, that circuit is broken. Power to the motor is cut, and the brakes engage. Instantly. No questions asked.
But of course, nothing's ever that simple, right? This long circuit creates a new, more subtle problem: voltage drop. Think of it like water pressure in a really long garden hose. The pressure is weaker at the far end. Well, electrical voltage does the same thing. In a super tall building, that safety circuit could be hundreds of meters long. If the voltage drops too much, the safety relays might not get enough juice to work right, which could cause a false stop, or even worse, a failure to engage when needed.
So what does this mean? It means engineers are basically obsessed with picking the exact right wire for the job. They have to think about the total length, the wire material, is it copper or something else, and even the tiny bit of current it needs. And safety standards, like EN81, they even demand a minimum thickness to guarantee that signal stays strong and the whole safety system stays robust. And just when you thought we were done with electricity, there's one more sneaky danger we have to talk about: grounding. That safety circuit is designed to be floating. It's not connected to the building's electrical ground. Now, if an accidental connection to ground happens, it can create a secret little shortcut for the electricity. This could actually let the current bypass an open safety switch, tricking the system into thinking a door is closed when it's really open. And that would effectively disable the entire safety chain. Oh, and don't worry, the call buttons you push are on a completely different circuit. A faulty button will never, ever interfere with this critical system. So as we start to bring this all together, you can see how all these different pieces, the mechanical, the procedural, the electrical, they're all part of this one single unified philosophy.
I mean, think about it. You've got the millimeter perfect precision of docking. You have the strict, controlled protocols for a bypass. You have the meticulous, almost obsessive design of the safety circuit. Every single one of these details serves one and only one overarching goal. There is just no room for compromise when it comes to safety.
And that really gets to the heart of it all. In elevator design, safety isn't just another feature on a checklist. It is the fundamental principle that guides every single engineering decision, every choice of material, every maintenance procedure. It's built on the cold, hard understanding that even the tiniest oversight could have consequences that are just not acceptable. So the next time you step into an elevator and those doors slide shut with that satisfying, perfectly seamless alignment, maybe you'll have a new appreciation for all those silent, unseen systems hard at work, that unbroken chain of safety that's designed, quite literally, to have your back.